Okay, so welcome to this NSM course on GPU programming with OpenACC. Uh, in this class, what we are going to do is to look at the overall GPU and overall ways in which people have found out why parallel programming is going to be useful. So it's more like going to be a more high-level introduction to GPUs in the first class. While we have kept half an hour after this 1 hour lecture to be the question answering session, what we will do is to do that will allow you to ask questions even on the way. Right? So if you have, since we have a small class, there are around 55 people registered, and the number of participants seem to be half of that. So feel free to ask questions anytime. You can just unmute yourself or make use of this chat. I'll be checking the chat once in a while. And we'll go along. I mean, feel free to be interactive. Okay. So, yeah, so the overall agenda of this course is to learn about this OpenACC, which is kind of a standard for programming the various kinds of accelerators. And GPUs is definitely one of the accelerators that we are aware of, and therefore we would like to see how OpenACC can be used to program GPUs. So overall agenda for the 12 days, which you are already aware of from the web page, is we are going to look at the GPUs, then some of the basics of OpenACC in the second lecture tomorrow. And then for next 4 days, that is February 3rd to February 8th, we are going to go deeper into some of the most important constructs in OpenACC, which will allow you to write in general OpenACC programs for GPUs and do most of the work. There are some of the specific optimizations which we might want to think about when it comes to OpenACC, which will probably go beyond this course. Nonetheless, we can discuss some of these as we discuss some of these constructs. February 9th and 10th, we are going to look at vector and matrix operations. These are going to be very common operations which we usually do. These are also many times quite data parallel. That is, there is a lot of parallelism, independent computations available in all of these, and therefore, and many of your applications are likely to be making use of some vectors or some matrices. So I think these are two definite important applications or domain of applications which we would like to target, irrespective of whether you are working in, let's say, aerospace or materials or mechanical or computer science. All of these vector and matrix operations are going to come along pretty often, right? February 11th is going to be a specific application. So we are going to take substitution cipher as a case study, and we are going to apply our learning to this cipher, and we'll see how we can parallelize some of these aspects of the cipher, which will also reveal how these constructs work together and where all we can apply optimizations, where all we can go wrong also. On February 12th, which is a Saturday, we'll have an exam at the same time, 5 to 6, which will be an MCQ exam. Most probably it will be on some sort of Google form where you will be able to judge your own understanding of this course, and that will mark an end to this. Okay. Any questions on this agenda so far? Okay, there is a question from Tony. Will you share the slides and recordings after the class? Yes, I'll be sharing both the slides and the recordings after every class. The recordings are anyway going to be visible, which I'll make visible, but the slides are, I mean, although I have a set of slides, I'm going to keep changing those as we discuss, because some of the questions I would like to incorporate those into the slides itself in case required. So therefore, I'll probably be making changes to these slides, although I will share the link to these slides. These are currently on Google Slides, so I'll share that link after the class. Nitin is asking, is familiarity with C++ helpful for understanding OpenACC? In this particular course, yes. In fact, I assume in some sense that everybody is kind of aware of C or C++. Definitely, OpenACC is also useful when you have Fortran. So your understanding of the concepts will not go wrong in case you are not so much familiar with C++. just that you will have to apply those concepts in the Fortran aspect also. I'll mention at a high level what kind of constructs you need to give when it comes to Fortran. I mean, the constructs are almost the similar, but the syntax might differ a little bit. I mean, you'll have to do bang dollar ACC instead of hash pragma ACC. Right? So otherwise, the constructs remain the same, which you can apply to usual for loops, etc. So I'm sure even if you are working with Fortran, this course is going to be helpful to you. Okay, so let's jump into the first lecture. So this plot, some of you may have come across, and in fact there will be more such plots which I'll be showing, because we are talking about the motivation behind using parallel programming as well as GPUs, and how it evolved, right? So therefore you might see some of these as we go along. But nonetheless, this is going to be a useful old plot, right? So although I'm talking about good old days for software, this plot itself is also old. So what does that mean, right? So the x-axis shows different years, and y-axis shows some instructions per second. That is the how many instructions you can execute for a particular, let's say, benchmark or your programs. For your program on a particular hardware, right, or on different hardwares. Let's say this is the maximum or the peak improvement or peak performance that you can achieve on any software that might be, or any hardware that is available, or maybe on Intel architectures or something like that, right? So that is not very important. What is important is that the reason why this is called as good old days for software is because you write your program, let's say C++ Fortran. I write my program and I optimize it the way I want. And let's say I have written it in 1979. Right? Maybe I'm taking a wrong example because many of you may not be even born during that time. But let's say that 1979 or 1980 is the time when I have written that software. What I do after that, okay, I compile it and run. And it took me 10 seconds on my hardware. It took me 10 seconds on my hardware to run that program, right, on a particular input. So far, so good. I am happy with that. That is probably the best I can achieve. And after 5 years, let's say 1984-85 time frame, what I do is I buy a new laptop or a new machine. And I take the same program, same source code. I compile it with the new software, new compiler, and I execute it on the new machine. Right? Earlier the time was 10 seconds. Now I see that the time is likely to get reduced to maybe 7 seconds. What did I do to achieve this? Maybe I spent a few dollars, few rupees to buy the new machine. But other than that, I didn't do any modifications to my source code, right, to the program. This means that I am actually getting nice performance improvement over the years just by improving my hardware. Therefore, I don't need to worry too much about the software improvement. Of course, there used to be a lot of work that used to go in software improvement also. But what this means is that I just improve my hardware and I will still get good software improvement, good performance on the new hardware. And therefore, these used to be called as good days for software, right? So maybe your manager would be very happy to buy. You can just tell the manager, oh, this program is very slow. And that's what your manager says. And you say, okay, you just buy a new hardware and that will be happy. The person will be happy because you have improved the performance. And this continued for some time, right? Late 90s or so, this kind of continued and we were getting a very nice benefit, right? So this can be summarized as this, that you get a lot of improvements in your software's performance, primarily because of the advances in the hardware, that is the architectural improvements. Some of the architectural improvements could be in extracting instruction level parallelism from your code, the instructions that are being executed on the hardware, or even the pipeline, or there is prefetching happening, or the cache organization has improved, or the size of the cache has improved, whatever are the improvements that are being done in the hardware. All of those are going to lead to this automatic performance improvement in your software. So this used to be the case earlier. And this continued, right? So again, the x-axis here, this is the second plot. X-axis here shows the years. Y-axis shows the frequency of the hardware. That is the frequency of the clock at which your core is running. and it shows it for two particular configurations, AMD and Intel. And the hope was that as the clock frequency is increasing, that means you are able to run multiple and multiple instructions, more and more instructions in a cycle or per unit time, and therefore you are, as the frequency increases, as the years go by, you are going to get more and more performance out of your same piece of code. And therefore we were hoping that early 2000 we are heading towards a brighter tomorrow, right? And this will continue. And some of you already know what happened after that. If you want to kind of pitch in and say what has happened, feel free to do that. Meanwhile, I'll take one question. Surya is asking, are there any practical practice sessions? I am not planning practice sessions because the time is limited. This is a small workshop. But what I could do is to give you some practice problems. And if required, we can conduct some practice session, actually even beyond this course. If somebody is interested, I can have some sort of practice session afterwards, because during this particular time, during these 12 days, we might not get enough time. But I'm sure there will be some people who will be interested in doing some better coding. So we can have some practice session just for the curious minds. Yeah, there is a question from Tony. Yeah, go ahead, Tony. Does clock frequency alone does not translate to performance, right? There are other factors. Yes, that is correct. Clock frequency was definitely one important factor, because, I mean, although the clock frequency per se, we view it as a kind of one aspect, but there are other aspects which actually improve, I mean, which actually result in the improvement in clock frequency also. But yeah, clock frequency alone is not going to lead to improved performance. There are other parameters, like we said, the prefetching improvements or other architectural features, maybe caching, maybe better branch prediction. All of these algorithms that we study as part of computer architecture, those are all going to be affecting the performance, not only the clock. But as long as the clock is improving, we are sure that the performance is also going to improve, because my computation is going to take certain number of cycles, right? My computation is going to require certain number of cycles. Now those cycles, if I finish in 10 seconds versus 7 seconds, I'm going to get performance benefit, right? So that is what was the main point here on this slide. Okay, good. That was a good discussion. By the way, if you are feeling shy in asking questions, you can ask those later also. If you are feeling shy in unmuting yourself and asking, you can use the chat. But in all my classes, my students keep asking questions by unmuting themselves, so you should also feel free to ask. There is no problem. All right, so I'll move ahead from here. So this was the case, and as some of you would have guessed from the title, we kind of ended up hitting a power wall, right? So what that means is, I'll show you on this slide. On the x-axis, I show what is the kind of chip size or the area that I'm using, or you can view it as the architectural improvements which are resulting in smaller and smaller boards, right? As you create smaller and smaller boards, the size of the number of things that you can put into that chip is going to reduce. And that means that they are also going to get smaller and closer to each other. Y-axis shows the amount of power that such a chip is going to dissipate per unit area, in this case per centimeter square. And this is in log scale, right? So therefore you can view that a linear is actually exponential, because there is a log scale on y-axis. And I start this line with the good old x86 CPU, let's say 80386, right? And then the amount of power that it used to dissipate was much smaller, and then 486, then Pentium came. And then people started realizing that the amount of heat that gets dissipated is actually quite large. At that time also, it was a large amount of heat. And some of you might have these laptops, right, which are running. If you actually keep your laptop on your lap, you will realize that after some time it starts heating up, and you will feel the heat, right? So therefore, that hot plate that I'm showing you on the slide is actually the amount of dissipation that can get triggered even if you run, let's say, simple programs like your YouTube or even Google Meet and WebEx, etc. This continued, right? So at that time, it was not a problem. Hot plate is okay. But then if such a trend was followed, then at some point in time, with this exponential increase in the power dissipation, the expectation was that the single CPU, single machine will dissipate so much heat that will reach uh, a, a place where the amount of heat dissipated will be equivalent to the amount of heat that is dissipated in a nuclear reactor. Right? That's a little too much, and of course, that is not going to happen. It's just that this projection was shown that if you follow this particular path, then you are going to dissipate a large amount of heat. And that if you continue, then you are going to generate heat that is equivalent to rocket nozzle. So you can't even probably hold your machine. And eventually will reach the heat which is going to reach the heat dissipated at the sun's surface, right? So there's extrapolation. Of course, nothing of this thankfully happened. But this shows that the amount of power was really a big problem, big concern when we were trying to follow this particular trajectory. And therefore, this problem is called as hitting the power wall. We changed the brighter tomorrow to something like this, right? So I was not showing you the complete plot. I showed you only up to 2004 or so. But beyond that, some of the processors which were planned with probably higher frequency, higher transistor count, those had to be cancelled because of this power problem. Right? You should be aware that this happened right around early 2000s. And that's one place, although parallel programming has been there since 70s or so, the importance of parallel programming kind of accelerated during these early 2000s when people realized that there is no other way than getting performance. And I'll show you that on our next slide. So what people found out, and you can see in this plot, again, x-axis shows different years and y-axis shows a log scale. And these are different counts, right? So what are these counts? One is the bottommost one, which I'll call as violet, is going to be performance per clock, or the amount of instruction level parallelism that I can extract out of my program, right? That will reach a plateau. That was also evident kind of, although there is a lot of research which happened in 70s and 80s to extract ILP out of your programs. But this is going to be limited beyond a point because ILP was kind of dependent on sequential programs, right? So we were writing sequential programs and we were trying to extract instruction level parallelism out of it. Now, how many instructions are really going to be parallel there? Because the way we write programs, we write sequential codes. The way our mind works, naturally we write sequential codes, right? There will be fifth instruction which is dependent on first and second instructions. Maybe there will be third instruction which is independent of the first and second. So maybe you can execute some of these instructions in parallel, but not all. And therefore the amount of ILP that you can extract was limited. If I go to the blue one that shows the amount of power that gets generated, and that was also reaching a plateau because I could not because of the power wall hitting area, that hitting problem that I showed on the previous slide. The clock speed also stopped working, stopped increasing because of that, although there was a very nice increase up to early 2000, but it also reached some sort of a plateau, which means that I could not clock my core at more speed than beyond, let's say, 3-4 gigahertz. That's it, right? So beyond that, I can't go. Otherwise, the chip will burn. The only thing which was possible, which people found was still legitimate and which was increasing every 2 years or so, was the number of transistors that you can push into the chip. But because of these problems, the issue that came up was that, oh, I have a large number of transistors on my chip, but at any point in time, I will be using 50% of them or 25% of them and so on, right? So you can use different parts of the chip at different times, but because of this power problem, I won't be able to use all of the chip at the same time, right? This was kind of a little disappointing because I'm paying for all these cores and then I can't use all these cores because of these power related problems. So what could we do to make sure that I cannot go beyond a certain ILP, beyond a certain clock speed, beyond a certain usage of power, was to, and still there are transistors which are unused, is to not go sequentially but make use of these for another core. Make use of these transistors for other cores. That means that I am going to build a multiple core machine on which I will be making use of these transistors, and these cores will help me improve the overall performance of my machine. Again, it's not that multi-core machines were not there earlier. Multi-core machines have been there since a while. However, the importance of multi-core rapidly increased after people figured out that this is going to reach a plateau. Right? So that is what gave us a lot of motivation to go parallel, and we started exploring parallel programming paradigms more often after these early 2000, and that is where multi-core programming became much more mainstream than it was before. All right, so I'll take up a couple of questions. Nishant is asking, what does ILP stand for? It stands for instruction level parallelism. That is the number of instructions that I can execute in parallel out of a given program. Right, so assume that, I mean, in this case, I'll assume a multi-core machine is already available, but let's say that you have large number of cores. Let's say that 1000 cores are available, although usually the multi-cores will have a few tens of cores, but let's imagine that you have thousands of cores. And then you have some set of instructions in your program, right? So there will be, let's say, a load instruction, then an add instruction, multiply instruction. At the assembly code, if you look at, you will see that there are a large number of instructions available. Which of these you are able to execute in parallel? Right? If you look at that, then you will realize that actually very few can be executed in parallel, if you think about it in this manner. This limited the instruction level parallelism that is possible. Although I am providing you with 1000 cores or maybe infinite number of cores, the amount of parallelism that you inherently have in your program is going to be maybe 4, 5, that's it. And therefore, you won't be able to extract enough parallelism by just following independent instructions. So this had to be viewed in a different way as we move to data parallelism, and we'll study that in the context of GPUs. Okay, thanks Jesh for that full form. Okay, so we'll move ahead from here. Again, x-axis shows different years, and y-axis shows different amount of performance that you get out of, or the peak that was achieved by any system in the world. Okay, that performance typically is used in something called as a flop. Right? So can somebody tell me what is the full form of flop?
Floating operations per second.
Okay, good. Thanks for that. Yeah, Suro has also written floating point operations per second. Abhishek says floating point operations. Yes, per second. Himanshu says floating point operations per second. Yes. So all of these are floating point operations per second. What does that mean? I am measuring performance of my program. I need some measure. One measure is, I'll say, number of instructions executed per second. Right? That is, or per clock cycles. That is also called as IPC for that matter. But what people figured out is that many of these high performance computing applications use a lot of floating point arithmetic. So why not measure it in terms of these floating point operations? I don't care too much about, let's say, the load store operations or integer operations. As long as my simulation specific floating point operation, if I want to simulate smooth particle hydrodynamics, or I want to simulate some biomolecular simulations, or I want to do some sort of number crunching using floating point operations on my matrices, then I need this floating point operation. I want to solve this linear system of equations. Right? So floating point operations are going to come in handy for all of these. Therefore, people started measuring this performance with floating point operations, and the number of floating point operations you can perform per second is going to give you approximate good performance of your system. Right? Because finally, I am interested in my own application. I am not interested in really instructions per cycle, which is a very vendor specific quantity, which might not give me enough performance benefit when it comes to my applications. So this y-axis shows this floating point operations in terms of, let's say, multiplied by 10 to the power 3. So that becomes kiloflop, megaflop, gigaflop, and so on. And what this shows is that at what stage our performance of any system peaked at these. That is, when did we achieve, let's say, kiloflop or megaflop in different years. So kiloflop, we kind of, initially itself we had good machines which had kiloflop performance, but we achieved megaflop performance, let's say, around sometime around 1970s or so. Then gigaflop, which was 10 to the power 9, we achieved sometime around 1980s. That was called as M13 supercomputer. And then there were other milestones that we started achieving. And the petaflop range we achieved sometime in late 2000, which were multiple GPUs which could achieve that around 2008 to 2009. For example, Cray and then GPU powered supercomputer. All of these were extracting this amount of parallelism petaflop performance out of these. That was 10 to the power 15 floating point operations per second. And then you would have heard this term called exaflop, right? 10 to the power 18 floating point operations per second. And we would like to reach there. That is called as exaflop. And it was expected that around 2019 or so we would reach there, and definitely in 2020. Unfortunately, we have not yet crossed that barrier, right? So we have not yet reached there. This is a projected performance from 2010. This image is a little old from AMD, but we are not there, but we are very close to that. So around 0.75 of exaflop we have already achieved. Now, from our previous discussion, you might wonder that is this really possible to be done by one machine? If this question came to your mind, you're on the right track. This performance cannot be achieved currently by a single machine. It has to be a farm of machines. It has to be a distributed setup of different machines which are working together to achieve certain performance, right? So that is what is being achieved by these systems. So the machines that we are currently talking about actually have millions of cores. Now, millions of cores are not going to be present on one machine. There will be multiple such machines connected together via some fast interconnect, which are going to work together towards a parallel system, which is going to achieve this performance, right? And does anybody know which benchmark or which program gets used by all these different top servers in the world to quantify this performance? Okay, Dhruva says Linpack. Anybody else?
Yeah, I have a question. Hello, am I audible?
Go ahead.
Yeah.
Ram, go ahead.
Yeah. So if you want to really compute the number of flops or floating point operations per a given program, then typically is it depending only on the arithmetic computations or something like possibly memory operations are also included in this?
Yeah, so good question. So just for everybody's benefit, I'll repeat the question that when we are talking about flops, are we concerned only about flops or other operations which might actually be more costly than the floating point operations? Do also those get included? Typically, since we talk about the peak performance in this case, we ignore the load store times, and only the floating point operations that get performed need to be calculated, which defines the peak performance. However, if we have to worry about the average performance, that is of the program, then all these other operations will also come into picture. However, I will, from my perspective, I will say that then the floating point operations per second is not the right metric to be used for such performance benefit. But when we are talking about flops, it's only the floating point operation. In fact, many times there may not be a program which will help you achieve, identify this very easily. Sometimes, depending upon your program, you might have to actually calculate the number of floating point operations in your program manually. unless you have some tool available, which can, because there could be arbitrary processing that you might be doing in between the floating point operation.
Right.
Okay. Yeah.
So which means that could be something like using these two parameters, one can even define something else that would eventually may give much more very close performance in reality, right?
That is correct. That is
Okay.
correct. In fact, yeah. So I'll also say that this flops is going to be useful when actually the program that we are targeting has actually uh, uh, most number of floating point operations, in the sense that the majority of the operations are actually floating point operations. If the for example, I mean, I'm just extending Rama's argument. Let's say I'm talking about some algorithm, let's say graph algorithm, which has a lot of load store operations, then flops is not the right metric to be used for such programs. Typically for these simulation based codes, we will have some initial loading of the data, which will require a lot of load store. Once we have populated our data structures, which are typically going to be arrays and matrices, those are going to be available for processing. And after that, we are going to release the results to, let's say, disk. This initial part and the final part where I'm actually accessing disk, I typically say pre-processing and post-processing, which I ignore from the perspective of this performance calculation. And therefore, most of my operations are essentially floating point operation, and therefore I can use this term. But if my processing in between is actually making use of lots of load store operations, then flops is not the proper metric. Right.
Sure.
Yeah.
Great.
Swapnil is saying HPL is high performance version of LINPACK. Yes, that is correct. Yeah, so LINPACK or HPL are essentially the ones that get used in this top 500.org. Some of you would be aware of this website. I just mention it. Okay, I have just mentioned it verbally. Swapnil is saying spec 2, not sure which exact version of spec is used. Yeah, so for the top 500.org, typically we don't use spec, but yes, spec is also another benchmark, which is a closed source benchmark, which gets used, or I mean, you need a licensed version of spec, whereas LINPACK is kind of a free program which you can run anywhere. So spec is also used for benchmarking. In fact, there are a large number of other benchmarking software which are available. However, for the performances of the supercomputers that we are talking about, we use LINPACK. Okay, sounds good. I'll move ahead from here. Feel free to keep asking these questions. So that gave us some sort of motivation to go parallel. What I'm going to tell you now is that are GPUs really useful? I mean, there is a lot of hullabaloo about GPUs, and then I can run all my programs on GPUs and neural networks. I can run training. I can do fast on GPUs, etc. Is it really worth it? I mean, is there really large difference between CPU and GPU performance? That is what this particular plot is trying to convey. So there is something called a single precision and double precision. Does anybody know what that single versus double precision mean? Okay, Tony is saying 32-bit versus 64-bit, right? So I'm asking these questions, but don't feel disappointed if you are not aware of the answers. This is not something which you should be aware of, but I'm just asking to have more and more interaction. So it's all right if you don't know these answers. So Tony says 32-bit versus 64-bit, which is what is called a single precision versus double precision. In fact, if you can relate it with respect to the float versus double types that we have in C, you'll be able to figure it out quickly. And that's why this is also called as double. So size of float is 4 bytes and size of double is 8 bytes. And Himanshu, as rightly has pointed out, it defines the precision of the floating point representation. That is, since you have larger amount of storage for storing a floating point number, you'll be able to perform more precise computations. If I say that, let's say, the distance between, let's say, Chennai and Bangalore is suppose some maybe 300 kilometer, right? In contrast, if I say no, it is not 300 kilometer, it is going to be 300 point something, maybe 300.5 kilometer, right? So that is being more precise. But if I'm using only integer, then I'm going to either say 300 or 301. In a similar manner, if I have to say 300.45 rather than 300.5, maybe I require more number of bits, maybe 300.456798, right? So this is going to require me more and more bits to represent this information. And if I have 8-byte representation, I'm going to specify, being able to specify it more precisely. And therefore, the computations that I perform using these floating point numbers will have better similarity with the actual output if I use larger and larger bits or more and more bits in my floating point representation, right? I'm again talking in the context of several simulations and several equations that we solve as part of high performance computing. Yeah, Swapnil is saying, yes, 4-byte versus 8 bytes is more appropriate as byte can have different number of bits depending on architectures. Well, yeah, we typically use a byte as 8 bits. So I actually meant it to be 4 bytes as 30 bits, but yeah, I take your point that maybe some architecture might have a very different number of bits per byte. I don't know, at least I'm not aware of other architectures which have more than or less than 8 bits. All right, so yeah, thanks Josh for that. The word size might differ. For example, when you say a word, typically it means 4 bytes, but depending upon the architecture, it can mean 8 bytes also, right? For example, size of int, if we print using our C program, it might be 4 bytes on some architecture, 8 bytes on some other architecture. Okay. Himanshu is asking, is being single precision the reason why commercial gaming graphic cards are not used in scientific computations? Well, the precision is definitely less. For example, yeah, so let me explain that point a little bit and I'll connect it with what we have been discussing. So floating point representation of 32 bits versus 64 bits will have different precision. And if I am using it for, let's say, gaming or graphics purposes, which allow you to have, let's say I'm doing some image processing or video processing, which allows me to perform approximations, right? I don't really need that double precision, very, very precise information. If that is my application, I might be okay using 4 bytes, right? What is the advantage I get by using single precision or 32 bits? Well, I lose on precision, but I gain on performance. And that is what this plot also shows, that if I use 32 bits, that is single precision, then I get better performance. That means I am able to perform more operations in one per second, 1 unit time. And you can, that's also one of the reasons that all these imaging software, in fact, imaging hardware also, they will be able to perform at a much faster pace if we are using this. So this is definitely one reason, Himanshu, that this is not going to be very useful for scientific computations. At the same time, I will say that there are large number of research works which actually make use of floating point arithmetic also. So while your final computations might still use a double precision, at least to get going with your numerical simulations, you can start with your own hardware which is using single precision. Make sure that it is giving you reasonable benefit, make sure that correctness is guaranteed, etc. And then, but maybe it is coming to a halt in fewer number of iterations, right? That is not something which you are expecting, because the double precision is going to probably require more and more number of instructions to, because you'll be able to set the threshold of your numerical computations, the diff across different iterations, across consecutive iterations, to be more precisely, right? So instead of saying my error rate should be 1.10 to the power minus 4, you'll be able to say that my error rate should be 10 to the power minus 7 or something like that. So definitely that is one reason, Himanshu, that this is not going to be very useful, but nonetheless it can be used for scientific computations also in a limited sense. So saying practically today byte is 8-bit, theoretically sure. If we design system based on different character set, that then ASCII, our byte can be different bits too. Hypothetically, if we design system based on ABCDIC character set or character set that requires just 7 bits or 10 bits, yeah, sure, that is possible. So you can design it that way. But then when we are designing the system, we also need to be careful about how the interoperability of that system is going to be. For example, if somebody is writing a program for your hardware, it might not remain portable. But yes, if you are specifically concerned about, yes, I am concerned about this particular set of bits and all my programs should adhere to this, then yes, you are right that you'll be able to have a different number of bits into the byte. Sure. All right. So I'll move ahead from here, but I hope this particular slide should give you that the difference in the blue versus green uh, lines is actually huge, right? So what we are talking about are different families of processors on CPUs in blue and of GPUs in green, and the difference is really large with respect to the performance. There is no log scale here, but you can see that the GPUs today can actually achieve very high amount of throughput, I would say, or I mean, in some sense, performance. Uh, that then can be achieved by relatively higher end CPU, right? There are differences with respect to performance, but there is also some sort of advantage of using a certain type of core, either CPU core or GPU core, for certain kinds of applications. Therefore, when it started, people started saying that, oh, GPUs are going to replace the CPUs and so on. That is not something which I would say, and in fact, that has not happened. But what is going to happen and what is happening is that people have started using CPUs and GPUs together, right? So different parts of your core might require different kinds of architecture, and therefore you should make use of these as a heterogeneous computation. Some part on the CPU maybe if there is sequential component or if there is parallelism which is limited to a few tens, maybe we should use CPUs. Maybe there is a lot of data transfer involved. If I want to get some small benefit out of GPUs, maybe I should not go to GPUs at all. However, if there is large data parallelism, the data is large and the amount of time that it takes is large, then yes, offload it to the GPU, right? So we have to, as a client of CPU and GPU, as a client of these architectural systems, as a programmer, you should not view that I am for CPU or I am for GPU, I am for Intel or I am for NVIDIA. Your job is to get the highest performance. I don't care who gives me that. If it is in combination with CPU and GPU, so be it, I'll do that. All right. So with that background knowledge, hopefully I'll not show more plots than this one. Maybe one-off plots I'll show later. But let's delve a little bit into various kinds of parallel platforms that we use today. And that is going to be also important from the perspective of not only this course, but your overall understanding of parallel programming, right? So if you have any questions on any of these items, please feel free to stop me and ask. So one of the important aspects of this is our CPU. Most of you would know that there are multiple cores in actually all the machines that we use today. Right? So, for example, our laptops are these days quad core or octa core and so on. In fact, some of your mobile phones might have multiple cores in them. These are all called as multi-core machines. And all of these share the common memory across all these cores. That means the RAM or the DRAM that we talk about, that is going to be shared across all the cores. If I, from a particular core, if I update a particular memory location, from the other core, I'll be able to read that memory location, right? So that is possible, and therefore we say that this is going to be a shared memory architecture. There is definitely going to be some small piece of RAM which is going to be local. Local meaning that is not going to be accessible or given to other cores, but that is more from the perspective of execution. As far as the whole RAM is concerned, all these addresses are actually accessible to all the cores. Right? There are some small amount of registers which are there locally for each core. Those are definitely going to be core specific. But by and large, this memory that we talk about is shared. Okay. The second type of parallel platform that we talk about is a distributed system. The one that we were talking about, where there are millions of cores, and we said that no, this is not possible to put millions of cores. You can put millions of transistors or even billions of transistors in a chip, but you cannot put currently millions of cores into a same chip. And so these chips are going to be distributed. That is, inside one big room, there will be multiple such machines kept. Of course, there won't be like the desktops that we see. These are going to be some rack mountable sliding large machines which are going to house multiple cores within them, and then multiple of such rack mountable machines are going to be connected via some interconnect. This connection leads to a distributed setup. What does distributed mean? Distributed means that yes, the machines are distributed, yes, that is correct, but the memory is also distributed. In contrast to the shared memory, where there is a single RAM which is shared across all the cores, in distributed setup or a cluster, the memory is specific to individual machine, right? There is no shared memory across two machines, and definitely no shared memory across all the machines. So therefore, this becomes a distributed memory setup, which is also quite useful, and the kind of and that means that if one machine writes to a particular memory location, that write is not visible to the other machine because the memories are actually different. If you want the data to be accessible from the other machine, you will have to send it via the interconnect to the other machine, and then the machine is going to have access to it, which means that there will be a copy of the data from one machine to another, or transfer of the data from one machine to another. And this data transfer across machines is called as a communication across these machines in a distributed setup. It turns out that this communication turns out to be a very important factor. Reducing this communication is important from the perspective of good parallel performance in a distributed setup. Higher the communication, the amount of computation that you do on individual machines, the benefit that you will get with this parallel processing will go on reducing if the communication starts increasing. Okay. Again, this part is not, I mean, both of these are not really important from the perspective of this particular course, but it is nonetheless important to understand as part of the overall HPC paradigm that we are aware of. The third one which we are dealing with in this course is called as a many core setup, or the graphics processing units or accelerators, which might have not only, I mean, in a multi-core you will have a few tens of cores, whereas on a GPU typically you will have thousands of cores available, okay, depending upon the capability of the GPU. And therefore this is also called as a many core platform. GPUs, the way we program, it actually turns out to be, there are similarities with respect to what we do with respect to a multi-core setup, because all the cores of the GPU are going to also share the DRAM. Which DRAM am I talking about? I am talking about the DRAM of the GPU. There is a separate memory of the GPU. There is a separate memory of the CPU. These both might be connected into the same, let's say, machine. There are GPUs which also are on chip with respect to your CPU. In fact, some of you might have these Jetson boards and so on, which will share the RAM with the CPU, right? So those GPUs are also possible. By and large, we are going to assume that the GPUs and CPUs have separate memories, but remember that, so these are called as discrete GPUs. But remember that there are integrated GPUs which will share the same memory as the CPU, and therefore communication across CPU and GPU turns out to be much faster. In fact, some of your mobile phones might have a GPU, and that is likely to share the memory with the CPU cores. All right. So any questions on these three aspects so far? Sandeep is asking, architecture-wise, will there be any difference in distributed systems versus multi-cores? Typically, the multi-core machines are connected together to form the distributed setup. There will be some similarities and some differences. The differences are that the shared memory communication turns out to be important in multi-core, whereas the communication, that is across machine communication, turns out to be important in the case of distributed setup. Architecture wise, I mean, you can actually connect even arbitrary machines together and create a distributed setup. But typically, these are similar machines, which typically your institute or company is going to buy, put those into a room, a nicely AC room, or maybe there is a water inlet where there may be a water cooled supercomputer into this room. And then all these machines are going to get connected with probably 100 Gbps interconnect. So the communication becomes much faster with this 100 Gbps link. And so that is going to be very different with respect to multi-core. And therefore, programming wise also, since there is basic architectural difference between the two, programming wise also there is going to be large difference between the way you view your programs working in a multi-core versus working in a distributed setup. And therefore, we have actually different frameworks which deal with these two. For example, for multi-cores, we have OpenMP or pthreads, whereas for distributed, we typically use MPI. There are ways in which you can generate, I mean, from OpenMP, you can run it on a distributed setup, or from MPI, you can run it on a shared memory system. But yeah, these, I'll say at a high level, these differences do exist. In case of typical gaming NVIDIA graphics cards, GPUs have dedicated memory as well. It shares memory with CPU, right? Well, I would say no. Typically, in the graphics cards, which are gaming based, that is, these are typically going to be used for gaming purposes. Only the discrete GPUs have separate memory. What we are talking about as a separate memory for the GPU, when we have, I mean, there are graphics cards which actually share the complete memory with the CPU. However, you are right, Tony, in the sense that there is a small amount of memory, not the actual RAM, but there is a small amount of memory which is going to be specifically used for graphics purposes. So that is also called as a texture, which is going to be specific to the GPU. The CPU may not be able to access that memory, or it may, I'm not sure, but definitely that is going to be something which is very different than the way it gets accessed on the CPU, right? So on the CPU, we typically access RAM in a linear fashion, whereas the texture is optimized for 2D or 3D processing, because many of our images or many of our videos require 2D or 3D geometry. So the texture gets optimized with respect to that, which is not the case for our typical CPU memory. Right? So that difference is going to be there. As far as discrete GPUs are concerned, definitely there is going to be a different memory than the CPU. I'll also say that even for discrete GPUs, there is something called as unified memory, which is going to be common across CPU and GPU, but that is only an illusion. It's not actual memory which is really common between CPU and GPU or discrete GPUs. It's more so handled internally. The communication between CPU memory and GPU memory is handled automatically by the hardware, right, or the architecture. So there are combinations of these, right? So although what I'm talking about are more generic things, there exist some very specific places where these things little bit are against what I have said. Tony is saying in what category it belongs, multi-core or many-core? The GPU will still be called as a many-core, and the CPU will still call as multi-core. But if there is shared memory across CPU and GPU, these are still called many-core because the number of cores is large, typically. But yeah, these are more like, let's say, a combination or a gelling of multiple architectures that we are seeing on the slide currently. You are right. In fact, I'll extend that argument a little bit and say that even a CPU-GPU system can be viewed as a distributed set. Why? Because CPU has a different memory, GPU has a different memory for integrated GPUs, and they need to communicate across a channel between them, which is also called as PCI Express bus. And therefore, this becomes very similar to the distributed set. Right? And the communication between these two should be as small as possible to achieve best performance. right? So I mean, these are traditionally how we categorize parallel platforms, but there exist systems which are combinations of these, right? We also call them heterogeneous, but anyway. Dhruvajyoti is saying SoC-based systems like, for example, the recent ARM chips in Apple machines have a unified memory at hardware level for CPUs and GPUs. Okay, I was not aware of this, but yeah, definitely that is going to be something which must be existing, right? So we will definitely have CPUs and GPUs sharing the common memory. In fact, that is also something which people have been wanting since some time, because I don't want to keep two copies of data. I load the data from disk and store it in the RAM, and then I copy it to the GPU, and then I need to keep these two copies consistent with respect to each other, right? So that also becomes a problem. Right? So it also leads to not only difficult programs but also error-prone programs, and therefore this has been a long-standing demand to have common memory between CPU and GPU, which is what some of the integrated chips where CPUs and GPUs are kind of on chip or at least sharing the motherboard will have access to. Himanshu is asking, does memory distribution happen at the RAM level or at a different level in the memory hierarchy in the case we are discussing? This memory distribution, I hope you are talking about a distributed setup. If it's a distributed setup, that needs to happen at the typically the communication level, which is supported in a, I mean, many times they supported in a library. The library is written in multiple levels. At the software level, we can use some library which is, let's say, MPI specific or which is implementing the MPI standard. But underneath, it has to make use of the communication channel. That communication channel might be physical, which means that there is actually a wire connecting two machines, or at the physical level, it could be wireless. That means these two machines are communicating across air. That is also one possibility. So the distribution can happen at needs to happen at multiple levels, but as a programmer, we will program it only at the software level. That is at the program level. By the way, we are almost close to, with respect to the lecture, we are almost close to completion of 1 hour. But as we said that this is interaction-based class, so we'll continue for some more time these particular slides, and we'll take up questions as we go along. So Josh is saying that there will be copying of the data from CPU memory to GPU memory and vice versa. Yes. He's saying hence memory distribution happens at the RAM level. Yes. So yeah, sure.
I was talking about that GPU case, not about distributed.
Sure. Thanks, Josh. So what Josh is saying is that, see, your data is finally going to be in CPU memory. Yeah, no problem. It's perfectly fine. So in case of CPU memory and GPU memory, you have this data, and therefore we would like to transfer this data from one machine to another. Now the memories are not connected. Therefore, we cannot transfer data directly. It has to go to one level down, maybe deeper, into the actual communication level. So the data from CPU RAM needs to be copied via a lower level place in this hierarchy into the communication channel. From that communication channel, the other party, which in this case is GPU, is going to retrieve the data in terms of certain bits and bytes, get that data copied into the GPU RAM, and then the software is going to make use of it. So all the way it will come down and go up, even in case of CPU and GPU. All right, so I'll just quickly finish my slides, and then we will take up more questions as they come along. So although these three are the primary ones that we use, there are others that we should talk about definitely. FPGAs is definitely one important piece today, which are, I mean, typically the hardware is non-configurable. Whatever you get, that's hardware, right? You can't change it. But if you can change some connection, some gate arrays, then it's possible that depending upon your application, you can tune your hardware such that it suits your software configuration, right? So after manufacturing, you might be able to change certain connections into this FPGAs to make those suited for your application. So that is rapidly evolving, let's say, paradigm, I would say, and many applications are making use of this. These are, again, those of you who have interest should definitely explore. Some of the OpenACC stuff you might be able to not directly run on FPGAs, but more and more frameworks or libraries are coming up which will allow you to run your code soon on FPGAs as well as GPUs together. Similarly, there are application-specific ICs. Typical these machines that we have been talking about are general purpose. That means you can run your numerical simulations also, you can run your biomolecular simulations also, you can run some aerodynamics flow or contact CFD simulation also. All of these you can run on the same machine. So these are general purpose, but then you can create a hardware which is very, very application specific or domain specific. I want to create a hardware which is going to run only machine learning algorithms, maybe tensor computations, right? That leads to application specific ICs, which can actually accelerate your application very well, but it might not be suited for other applications. So if you are interested in that, you might be able to even take advantage of these ASICs to improve the parallel performance. And then a combination of all of these, which is what happens in many companies and many research works, is the heterogeneous system, which will have a combination of, okay, there will be a distributed setup of multi-core machines. Each multi-core CPU is going to house one or more GPUs in them. Some of the CPUs might also house FPGAs. There will be some application-specific ICs on some of the machines, which will trigger some very specific computations. Let's say I have a large application, some of that is performing TensorFlow computation, so let me run those on tensor cores, whereas some of that is data parallel, let me run it on GPUs. Maybe there is, and all of these are running on different machines and so on. So all of this is possible in a heterogeneous system, and therefore we also have different kinds of software architectures to deal with these different machines, right? Usually one size fits all doesn't happen, or it cannot extract all possible benefits out of these seemingly very different platforms. And therefore there is large work that is going on currently to support at least some of these into as part of a library or as part of the some languages, etc. Okay, I will yeah, as far as, so I was talking about the hardware part, let me briefly mention about the parallel programming paradigms. So multi-core system is typically programmed using frameworks like OpenMP, Pthread, Silk. You can use Python, you can use even PHP for that matter, for running things in parallel, etc. But more high-performance computing codes are typically run with one of these OpenMP, Pthreads, etc. So the way it looks like, this box, orange box, it shows one machine in which those vertical lines shows multiple cores, and this blue box shows the memory that is going to be common across all of these, and therefore we call this as a shared memory system. Multiple such shared memory systems are going to be connected, and note that every two machines might not be connected. Every two machines might not be directly connected. Those might be indirectly connected, and there is no shared memory across these. There is a distributed setup. Typically we use MPI to program these at the lowest level, but there are higher level frameworks like MapReduce and Hadoop, which you might have used. All the cloud computing setup which runs on a cluster will make use of some underlying standard like MPI or something else to program these distributed machines. And then CPU GPU setup, which can be programmed using CUDA, OpenCL, OpenACC, typically consists of these two boxes, which have different number of cores and possibly have different amounts of memory plus different memories altogether, and they are connected via some sort of interconnect, which can transfer data between CPUs and between CPU and GPU. These two will also be called as devices, which means that you are able to communicate across multiple devices using this interconnect. Sometimes the CPU is also called as a host, and the GPU is also called as a device. All right, if there are any questions, I can take those up now. Otherwise, I will move ahead in the slides till 6:30. Okay, Abhishek is asking, in distributed system, if two machines are not directly connected, then data is hopped between multiple machines. Yes, that is possible. That you might have to actually go a long way before you can reach the other machine. For example, here at least there is some communication. I mean, I'll be able to reach from any machine to any machine in, let's say, 4 hops or so. Right? And that is the maximum you would like to communicate. But you may not have those intermediate links, and then you can have some sort of a ring. All the machines are in a ring network, and there n by 2 is going to be the latency that your communication might involve to go from one machine or one hop to another. That's a good observation, Abhishek. Okay, so if there are no further questions, I will move ahead from here. So this should give you a reasonably high-level idea of different kinds of parallel programming paradigms that we have, as well as the parallel architectures that we have, in case some of you are unaware. I mean, it is important that we all are on the same page, because this high-level idea is going to be important when we are actually programming with OpenACC. Right? So I'm just expanding or zooming in into that CPU-GPU part, where that communication bus is also called as PCI Express bus. And as you can see, there are 2 different memories that we have. This is primarily for for discrete GPUs that I'm talking about. So this RAM is going to be different. That means that a variable which is present in the CPU memory cannot be accessed directly from the GPU. If you want that variable to be accessible into another GPU, into another memory, you'll have to copy it, right? So think about it this way. I mean, there are programs that people write, especially in CUDA and OpenCL, where you might forget this thing, or you might not copy the memory across these. I mean, it looks very obvious here that how can I access a variable which is there in CPU from GPU, but believe me that that does happen. When I teach CUDA programming at IIT Madras, initially students do commit such mistakes, right? And we all do when we are learning CUDA or OpenCL programming. I'll give you an analogy. For example, if I tell you that go to room number 25, okay, I'm telling you go to room number 25. Let's say you are in electrical department, you will go to room number 25 of electrical department. If I tell you go to room number 25 and you are in materials engineering, then you will go to the room number 25 in materials engineering. But these 2 rooms are different. And if I say that the treasure is kept, maybe your answer sheet or grade card is kept in room number 25, then it depends upon which department I am talking about. And this CPU GPUs actually are 2 different departments. When I talk about a particular memory address, that memory address is probably going to be present in both of these, but doesn't mean that your data is going to be residing in both of them. Your data is going to reside in only one of them, and therefore I should be careful while talking about the data and its address when I am dealing with CPU GPU which have separate RAMs. Thankfully, OpenACC automatically copies data across CPU and GPU, and that is going to ease out your programming, which unfortunately not the case by default in CUDA or OpenCL. But there is a downside to that. Can somebody think about that? If OpenACC is automatically copying data across CPU and GPU, what could be the downside of that? Nishant is saying memory requirement. Himanshu is asking bandwidth hungry. Rajana is saying memory usage. Swapnil is saying security. Okay, all of these are actually valid concerns. I was thinking more from the perspective of performance, but let me expand on each of these a little bit. Yeah, so memory requirement is not really going to be higher as such, because you will require the data copying across CPU and GPU. So the amount of memory will not increase, whether you do it manually or automatically. Is it going to be bandwidth hungry? Yes, that is possible, because now let's say I am writing to a large array, right? As soon as the array is written completely, I would like that to be copied to the other device. But if this OpenACC is doing it automatically, maybe after I write, let's say 8 bytes of data or 32 bytes of data, maybe it will get copied. And there will be multiple such transfers happening as I keep writing more and more. Right? So as a programmer, I know that it should not get copied so often. But then, as a novice programmer or as a domain expert, I don't really want to get into whether it is running on CPU or GPU. I don't care. As long as you are parallelizing it, I am happy with that. Right? So OpenACC was meant to be with that philosophy that even a science person who has full domain knowledge, he or she is an expert in the scientific computation, the physics of it or the biology of it and so on, but need not be an HPC expert. So even for such people, it should be possible to write their codes and parallelize those on the accelerator. So with that philosophy, this automatic copying is going to be happening. So yes, so the memory usage is not going to be high, but the bandwidth might get utilized more, and in fact, because of which the performance might actually reduce. Is security going to be a concern? Yes, security is going to be a concern even as soon as these automatic things happen. But security is something which we will probably not worry about in this course. It's a different beast altogether. It's definitely an important aspect, especially when we are talking about cloud computation, where I mean, all our programs are running together on different machines. Maybe multiple programs might be running on the same machine unless I have created some sort of container out of it and so on. So all of these security issues definitely are real and people are working on it. Yeah, but we'll not worry about that in this course. We'll worry more about performance. Dhruv is saying maybe unnecessary copies. Yes, there is a possibility of unnecessary copies going to happen. Okay. And we can so although OpenACC can automatically transfer data, what we could do is that whenever we are aware that such automatic copying can create problems, it will result in unnecessary data transfer, we can help the compiler generate only the required communication, at least minimize that communication or data transfer as much as possible. So OpenACC will help us do that as we go along. Okay. A typical GPU program flow is going to look like this. I'm going to show 5 steps pictorially. So the first thing is, okay, let me show you the architecture. We have this CPU, then there is a GPU. CPU is typically associated with a disk on which there is a file system, and I'm going to load some data from this CPU, from this file system into the CPU memory. Sometimes I might generate data randomly, or sometimes it might be coming from some socket or a network socket, etc. Whatever, there is some way in which CPU is receiving this data, which is getting stored inside CPU memory. Once that is done, some of that is going to be useful to be processed on GPU. And let's say I have identified that. So the second step is to copy this data from CPU memory to GPU memory. Once I have this available on the GPU memory, I'm going to run some function on the GPU which will process this particular data in parallel using multiple threads, and I'll get the result out of this in the GPU memory. After this, I'm going to copy the result back from GPU memory to CPU memory, on which I can start processing further. And that processing further could be dumping the data to a file, printing it onto the screen, or it might require further GPU computation. So from step 5, I might go back to step 2, where I might want to process that data again for the next step, or maybe I want to process next data on the GPU and so on. Right? So all of these are, this is a high-level picture which you should remember when we are doing OpenACC programming, so that you know that steps 2 and 4 are actually happening. You should not imagine that, okay, I'm just offloading it onto the GPU, it will run, give me the results back. Oh, then why is the execution time so large? Because there is this 2 and 4 steps are happening, which are not computation. This is an extra baggage, and therefore we have to minimize the amount of time we take in 2 and 4. All right. Okay, so which GPU vendors you are aware of? Which all manufacturers are there for GPUs? Okay, NVIDIA, AMD. Himanshu says, Abhishek says NVIDIA, AMD as well. Okay, are there more? Okay, Swapnil says Qualcomm, ARM, very good. So NVIDIA and AMD are definitely two big players in this market where we have GPUs coming from them, but then there are lots of other players which might not call their GPUs as a GPU, but these are still graphics processing accelerators, right? So definitely Qualcomm, Snapdragon, ARM are definitely having their own GPUs, but there are actually other vendors because they don't call it as a GPU. We might not view them as such, but their devices, for example, their smartphones or other devices which they might create, will probably have these GPUs installed in them, right? So some of these we are aware of, but there are others like Broadcom, Matrix Graphics, and even Samsung, and there are others which have their own accelerators. Need not be always GPUs, and not all of them will be OpenACC programmable, or not all of them will be CUDA programmable or OpenCL programmable as of today. But they will have their own APIs, or there will be libraries using which you will be able to program them as part of their, let's say, some sort of SDK might be provided. May not be to the end users, but maybe to their partners, which are licensed software and so on, right? So you should be aware that there are other players in the market, but definitely NVIDIA, AMD, Qualcomm, Intel, ARM, these are the primary vendors. Similarly, there are languages which we use for GPUs. For example, CUDA, OpenCL, and OpenACC. Just a high-level brief on these. CUDA is proprietary and it is NVIDIA specific. You might hear of CUDA much more often than other languages. That's also because NVIDIA is really a big player in this space. And although CUDA is NVIDIA specific, I mean, so it's actually giving very good performance with respect to the NVIDIA GPUs. OpenCL is the other side where it is open computing language. It's not at all proprietary. And it's supposed to work across all computing devices. That way it is universal, right? Think about CUDA as Windows and OpenCL as Linux in the high-level sense. People have been saying that OpenCL is going to replace CUDA and will do all your acceleration in OpenCL and so on. But I have been hearing it since more than 10 years now, but it has not happened. So it's probably best to say that, okay, both of these are going to stay for some more time together. Like Windows and Linux still exists, right? So similarly, CUDA and OpenCL might continue to exist for some more time. And maybe we should know both as of now. Okay, OpenACC is very similar to OpenCL in the high-level philosophical sense, but it is primarily for accelerators, not across all the computing devices. However, the way OpenACC is evolving, it actually can be used for even a multi-core processing, right? So you'll be able to write your sequential code, you add your OpenACC pragmas, and you will be able to compile the code for multi-core setup, right? Without making any changes to the code. So that way also it will have some let's say use case even on the CPU, right? But we primarily use it for accelerators. At least it was designed for accelerators. I will also mention that a lot of philosophy of OpenACC is derived from OpenMP, which is the parallel programming paradigm for CPUs. But of course, there are some quirks, and there have been some efforts to make OpenMP run on, at least the newest version of OpenMP run on GPU. So that is also going to come. I mean, that is currently in the let's say beta stage. I would say it's accessible. You should be able to use it, but it's not fully functional yet, right? So that is definitely another interesting thing that is going to come. Apart from these high-level languages, there are interfaces or libraries which are provided. For example, you can write PyCUDA. That means from inside Python you can write some CUDA functions. There are converters which are able to convert some of your Python code into CUDA code, or some of your JavaScript code into OpenCL, and so on. So all of these interfaces or libraries or frameworks are also available, which can help you run your codes or in different languages on the GPU or on accelerators. Maybe I'll discuss this quickly. When it comes to GPUs, I'm showing two configurations of NVIDIA GPUs, P100 and V100. Does anybody know what does P and V stand for? Okay. I can take these slides even later, but if you have any questions, feel free to ask those now, because we are almost close to the end of the class, next 7-8 minutes or so. Dhruva has said Pascal and Volta. Good. These actually are correct answers. So this P100 is a Pascal style family of GPUs, right? So these are different families of GPUs from NVIDIA. This is from Pascal family. So P100 is one such GPU. V100 is Volta GPU belonging to this category. The hardware is very different across these, and Volta GPU is the later family than the Pascal, and therefore the number of hardware units, typically the amount of performance that you can achieve, number of cores, etc., is going to be much larger in the Volta GPU. So I'm just showing these two typical configurations. Some of the things that should be concerning you right now is number of CUDA cores. When I said that our multi-core machine will probably have a few tens of cores, typically you might have heard about quad-core, octa-core, but some of the server-end machines will have, let's say, 8 cores, 32 cores, maybe 64 cores also. But the GPU, one GPU might have, let's say, over 3,000 or 5,000 number of cores also. Some of the tensor computations can happen on Volta, which is not supported in the Pascal family. You can look at the peak double precision performance, that is flops, achieved with this Volta GPU. It's almost 7.5 teraflop. Just to compare with a high-end CPU, typical high-end CPU might have a 3 teraflop performance coming out of it, peak performance. And therefore you can see that the amount of performance that you can get out of these many cores is really going to be large. One might say that this is very strange that you have these 32 cores and you get 3 teraflop, and you have this 5,000 cores and you get only 7.5 teraflop. Well, all these cores are, I mean, one should not directly compare between these CPU and GPU. The kind of cores that we have are very different. The kind of architecture that we have in terms of memory as well as caches is very different. The amount of data parallelism that you can extract will also be very different between CPU and GPU. But this gives you some rough estimate of what is possible. Final thing is about the GDDR, the onboard memory, that is the RAM that is available. Typically, these RAMs are currently small for GPUs, 16 GB, 32 GB, maybe 48 GB in some of the latest versions of the GPUs. So that is going to be much smaller. You would have heard of several hundreds of GB for CPU memory. So there, the CPU is likely to be winning in terms of the overall memory size. Himanshu is asking, what is compute capability here? Compute capability is a number, major and minor number, which specifies what are the functionalities that are provided by a particular hardware. For example, in this case, we say that compute capability 6, which means that there are certain functionalities which are supported in compute capability 6. Maybe it does not support tensor computations, but maybe it supports atomic instructions. Maybe it supports a number of threads which we can run in one gang to be 1024, something like that. So there are certain capabilities of the hardware, and when we are compiling a code, we need to compile for a particular hardware. Right? The same compiler could be used for compiling for P100 also and V100 also. but I need to specify that, oh, my program is making use of these functionalities which are available only in Volta, not available in P100. So I can specify that, oh, the compute capability with which I should compile my program should be 7.0. Right? But then why can't I just compile with the highest compute capability? Well, maybe you don't have the corresponding GPU running. I mean, compilation is one thing, but you also need to run that code. So if I compile it with 7.0 and run it with P100 and it is not compatible, then likely that you will get a runtime error. In contrast, if I compile it for 6.0 and run it on Volta, it will still run. Usually these GPUs are backwards compatible. So that's what compute capability means. Okay. Any other concerns? All right. So I'll just quickly wrap up now. This is yeah.
Sorry for the interruption. Yeah. In the previous case, when we run, when we get the code, when we compile the source code on P100, try to execute the same thing on V100, possibly the architecture, the instruction of set architecture might be different, right? Or
yes, it can be different, but typically these are backwards compatible, and therefore you will be able to run it for on Volta also.
Okay, I see. Okay.
Yeah. Sure. For example, Kepler, if you have optimized it for Kepler, you will be able to run it on Pascal as well as V100.
Okay. Okay.
Okay, so we briefly looked at the high-level aspects of parallel programming, and we looked at, let's say, multi-core setup, distributed setup, what are the many-core architectures, how they look like, etc. And I briefly touched upon what are the different softwares or libraries that we use for using some of these machines. For example, OpenMP for multi-core, MPI for distributed, maybe CUDA, OpenCL for GPUs, etc. We then looked at some of the configurations towards the end of the GPU architecture and how these memories are separate, etc. Plus, we also discussed lots of questions that some of you have asked. And with that, we will kind of wrap up for today's lecture. In tomorrow's lecture, we are going to look at basic hello world program of OpenACC, getting it compiled and running on some GPU. Right? Note that OpenACC is kind of, there will be some small issues that might come up depending upon your GPU. If you have tried it out yourself on some GPU, well and good. Otherwise, if you want to try it and ask questions tomorrow, feel free to do that. And we'll be able to sort those out. If we are unable to sort those out or you have questions later, feel free to post it on the Google group, and either me, Josh, or even some of the other attendees who have knowledge about it, they will be able to answer these questions. Okay. So the question here Nishant is asking is, can we get a recording for today's lecture? Yes, I'll post it in the same sheet that I have shared with all of you, and a link to this will be available there. All right. So if there are no further questions,
can I have a quick question?
Yeah, sure, Ram.
Yeah, this is from the very beginning slide. Somewhere when you talk about this heat dissipation, for instance, if one core has 1,000 transistors, and having these 1,000 transistors in one core, and having two cores in a machine, or the other version where 2,000 transistors can be in a same core.
Right.
Right. I mean, space-wise and all, it looks very similar, or possibly even a bit lesser than the isolated ones. But I mean, how do we convince that the power dissipation reduces when we have two different cores rather than in a single? The circuit, whatever is replicated in these two cores, essentially we are keeping in. If you want to keep in a single core.
Right. Yeah, so these are definitely going to be on the same die, but definitely they are going to be spaced out compared to what we are going to have for a single core. And therefore, you are right that If we space those out, then the power dissipation is going to be smaller.
Right.
That's one thing. The second aspect is that, I mean, although we will talk in terms of peak performance and they will be executing the same, probably the most prolific arithmetic instructions which generate the largest heat. Typically, it so happens that since these are multiple instructions, multiple data paradigm, different cores are actually running arbitrary computations, and the hardware or the ALUs or even the other parts, let's say even some of the local caches which are probably getting used for one core are not getting used by the other at the same time.
I
And
see.
therefore the power dissipation is likely to get reduced in such aspects.
Okay, good. Oh, so which means essentially those are inactivated in some sense, right? Okay.
I mean, I wouldn't say that these are inactivated, but yes, one can see that these are kind of independent entities now.
Right.
Right? Yeah.
Okay.
Nishant is asking, is it possible to test or code it on Mac M1? I am not sure about this support, whether it is supported on Mac. If anybody has tried it, well and good, but yeah, I have not. Actually, I am not sure if it is going to support Mac. Okay, Dhruva is saying no, direct no. So I am not sure if you will be able to run it on Mac. All right, I don't see any further questions, so I'm going to stop the recording now, as well as we will